welcome back. In this video, we're going to look at Hess's law and how to use it. So Hess's law is an indirect way to measure enthalpy change. Usually in chemistry class, we can use calorimetry to measure enthalpy change, but sometimes you come across a reaction that can't be duplicated in a lab or even in a calorimeter. So we have to have an indirect way to measure enthalpy change. So Hess's law is an indirect way to measure enthalpy change. And the way that Hess's law works is that you have a desired equation. So in this case, in the example that we're about to do, this is the desired equation. We want to know the enthalpy change for this equation. What you do is you take the sum of all of the equations that make up this equation, and you take the sum of the enthalpy changes. So it's the sum of the enthalpy changes of individual reactions that make up the desired reaction. So if you're trying to solve a Hess's law problem, you'll be given the desired equation. This is what you're trying to solve for. And you'll also be given multiple equations, 2, 3, 4, or maybe even more than that make up this equation. And we have the enthalpy changes for all of those. So we're going to manipulate all three of these equations so that when we add the sum of all of them, it will be equal to the desired equation. And at the end, we'll add the sum of all of the enthalpy changes and measure that as well. So we can start with the first equation. We have oxygen difluoride, and in our desired equation, we have oxygen difluoride in the reactant side, but we have 2 moles of it. So what we're going to do is multiply this whole equation by 2 so that we have 2 moles of oxygen difluoride. And when we do that, we'll also have to multiply the enthalpy change by 2. So our whole goal here is we're going to manipulate each of these equations in such a way that when we add them all together, they will equal our desired equation. So that's why we had to multiply this by 2. In the second equation, we have sulfur tetrafluoride, but we have sulfur tetrafluoride on the product side of our desired equation. So we're going to have to flip this equation. We need the products to be in the reactant side and the reactants to be on the product side. Whenever you flip an equation, if you're ever using Hess's law and you flip an equation backwards, that will actually change the enthalpy value to the opposite sign. So here we have an enthalpy change of negative 827.5. That means when we flip the equation, the enthalpy change will be equal to positive 827.5. And then for the last equation, we can see on the reactant side, we have 2 sulfurs. And here, sulfur is in the reactant side, so that's nice. But we need to multiply this whole equation by 2 as well, because we need a coefficient of 2 in front of the sulfur, which means we'll also have to multiply our enthalpy change by 2 as well. So now we're going to add all of these equations together using the manipulations that we wrote out. So I have 2OF2 plus 2H2O yields 2O2 plus 4HF. And my enthalpy change also needs to be multiplied by 2, which gives it a value of negative 553.2 kilojoules. The second equation, I'm flipping it. So I have 4HF plus SO2 yields SF4 plus 2H2O. And my enthalpy change is 827.5 kilojoules. The last equation I'm multiplying by 2. So I have 2S plus 2O2 yields 2SO2, and my enthalpy change is equal to negative 593.8 kilojoules. So let's make sure that our equation is what it needs to be. We're going to add all of these equations together to make one larger equation, and we're hoping that it matches up with our desired equation at the top. So if we have 2 of the same things on the reactant side or 2 of the same things on the product side, we would add those together. But if you have something that's on the reactant side and on the product side of another equation, you actually subtract those. So I will show you what I mean by that. We have 4HF on the product side here and 4HF on the reactant side here. So they're on opposite sides of the arrow, which means we need to subtract those two. So 4HF minus 4HF is 0. So we're just going to kick that out of our equation completely. We have 2O2 on the product side here and 2O2 on the reactant side here. 2 minus 2 is 0. So we're kicking those out of the equation as well. We have 2H2O and 2H2O on either side of the equation, so those also get kicked out. And now I'm just left with 2OF plus 2S yields SF4 plus 2SO2. And if we add all of these enthalpy changes together, we should get negative 319.5 kilojoules. So that is the answer to this question. We can double check that our equation matches up with the desired equation, and it does. It matches up with the desired equation. So our enthalpy change, I could write the answer here, is negative 319.5 kilojoules. I hope this was helpful. If you have any other questions, let me know. Check out some other videos on my channel. Thank you so much for stopping by.